Hello and welcome back to the second episode of our workshop series, Microfluidics and Business. And my name is An. I'll be the coordinator of the episodes today. Today, we'll be talking about the best engineering practices for fast and scalable solutions. And we have our frequent speaker, Mark Gilligan, who's the CEO and founder of Black Sheep Power. And we also have an expert engineer, especially for this topic. It's John, who's Black Sheep Power Chief Technology Officer. So for some of you who might have been with us in the first episodes, like you already know the format, in the first half of the workshop, then I'll raise some questions to the speaker that you send to us in advance. And in the second half, we'll have questions from you from the floor. So you can raise your questions throughout the episodes in the Q&A box. And then in the second half, if we have questions from the floor, then I'll unmute the person who asked the question so that you can discuss with our speakers directly. Yes. So with that, welcome everyone, and thank you, Mark and John, for joining us for today. Mark and John, to kick things off, could you both introduce yourself and maybe share some initial thoughts when you first came across this topic?
John, do you want to go first?
Yeah, so my name's John Briant. Thank you very much for the introduction, Anne. As you mentioned, I'm the Chief Technology Officer at Black Sheep Power. My background is mechanical and manufacturing engineering, so I've always been really interested in how things are made and especially how you develop products so that they are fit to be made in large numbers, or indeed in small numbers too. What did I first think of when I heard this topic? Basically, I thought, well, that sounds right up my street. It sounds like a topic that I've been interested in for more or less my whole career.
Yeah, and I'm Mark Gilligan. I have been part of the kind of creation of the microfluidics industry over the last 25 years, and originally was an aerospace engineer a long time ago, working in Formula One and aeroplanes. Went through developing the first DVD players at Philips in the Netherlands. Lived in the US developing mail handling machines, and then ended up in technology consulting. But anyway, I started a group of companies about 25 years ago, which included a microfluidics company called Dolomite Microfluidics and others, and built that up over the period until 2023 when I sold my group of companies to a company in the US. Anyway, and since then have been building Black Sheep. I think similarly to John, that I have originally been an engineer and been working in R&D and product development and manufacturing pretty much my whole career, which is now well over 30 years. And so yeah, it's a very interesting topic, and there are lots of ways of doing it wrong and very few ways of doing it right. Basically, there are lots of mistakes to make, and yeah, so and there's no perfect answer, but anyway, I think that it's a very interesting topic.
Yeah. I know you are both very passionate engineers, but the series is about microfluidics and business. So in your sharing, please also keep the business side in your answers. Okay, so maybe we'll start with a rapid fire question. Do you still remember what was the first product you ever developed for a business? And then what is your favorite product you have ever created? Mark?
I guess, well, I mean, I did work on airplanes and Formula One cars, but I don't necessarily see them as quite products in the way normally. I think the first thing I worked on that I properly regard as having developed a product was a mail handling machine. My favorite product, yeah, that's interesting. It's probably the Nadia system, which was a microfluidic single cell genomics platform, one of the first ever. Yeah, so that was a really neat product.
For me, my first product that I ever developed for a business was an asthma inhaler. I've actually worked on a few of those in my time. My favorite, can I have two favorites? One of my favorites was a surgical contraception instrument. and another favorite was a microfluidic mixer. And that latter one, the reason it was a favorite was because I kind of invented it whilst doing something else. The point of the project was something else entirely, and we needed to do some mixing. But then this mixing thing that I'd invented turned out to be really useful in lots of different areas.
But that mixing technology that John developed in around 2005 has gone on to still be in products today. There is still exactly the same geometry is being used today in relatively high volume manufacture in products that are sold.
So I can see different products has their own stories, but now thinking about a business who want to build a new product, people usually talk about the minimal viable product. So what is your definition of a minimal viable product? And what would you consider a good MVP and how to measure it?
Well,
yeah.
Okay, you go first, John. That's fine. You go first.
I guess I was just going to say that it's actually really difficult, especially at the beginning of a project, to know when you get to the end what's going to be the minimal viable product. So I think you have to really understand what value your users are going to get out of what you're developing, and your minimal viable product is something that really clearly expresses that value, but doesn't add other things that are unnecessary. And yet those other things, you can trip users up by not making the other things good enough. And so your minimal viable product has to express the value, and everything else has to be good enough that it's not a distraction or not going to make everything go wrong.
I think the other thing is that the state of the market for the company developing a product is very important. So if you look at something like a car, for example, if the minimum viable product of a car is something with some seats, some wheels, and an engine, and it moves forwards just about, well, that might have been okay 120, 130 years ago as a minimum viable product. But today, because there's been over 100 years of cars in the marketplace, that isn't a minimal viable product. You'd have to have quite an advanced car to be a minimum viable product that demonstrates some movement forwards beyond the state of the art today. Whereas if you're entering a market where there isn't anything at the moment at all, then you can have a relatively simple variant of a minimum viable product, which is just enough to prove that there's something here that's worth the customer buying for early adopters, and also proves to you, the company, this is actually something that is interesting to the marketplace. And you can understand some of the market behaviors and the people and the users and things like that. So it isn't a very easy question to answer, as John said, but it very much depends on the market. So it's more of a commercial decision than an engineering decision in some way. It's not really an engineering decision in many ways.
I don't think it's an engineering decision at all.
So from the favorite products that you've developed, if you think back about those products, what was the process for you to create the MVP?
Okay, so if we think about that surgical contraception device that I mentioned, the predecessor device was kind of sub MVP. It hadn't been engineered well enough, and it did things wrong, like it broke. If you operated it wrong, it would snap in your hands, which is a disaster if you're in the middle of a surgery. And it was really awkward to use. It kind of required your hands to be kind of contorted into weird shapes in order to use it. And so actually in that situation, we had a sub-minimal viable product, a bad product that was failing. The other thing that was failing about it was the production yield. They were having to throw away about 50% of all the product because of quality issues. And so there we had to focus on the value of the thing was still there. We had to focus on fixing everything else that was making the product fail. As I mentioned, all those other things have to be right enough that the thing is useful in the hands of users.
My answer for my favorite product is actually quite different in that the way that the companies I used to run worked. So effectively speaking, in the microfluidics industry 20 something years ago, there weren't really any people that had any products, not really. There were people doing R&D in universities, and there were people who had services to make chips or something or other. But I had a very strong mantra at the time, which was you have to put a part number and a price on it and put it on your website, and then people know that thing you can have. It's not just okay to say we have these capabilities. Now, the way that we did that was we didn't just have chips, we had connectors and pumps and microscopes and all kinds of things that we gradually fleshed out starting from around 2006, 7 onwards. And we ended up with a catalogue of Lego-like componentry. The reason why this is relevant to a minimum viable product is because it is useful to have a connector between a tube and a chip. And that's a minimum viable product in itself. But when you look at higher order applications, the way that we address those higher order applications first was to put a Lego set together, the collection of pieces that are needed to address that application. And the way we worked out those applications were interesting was because people came to our website and said, we're interested in these spaces, or our own team thought there was an idea of an application, or somebody else in an academic environment published a paper on a given area. And so we kind of established some understanding of an application being interesting, put a Lego set together. And if the Lego set sold with a collection of chips and pumps and connectors with the instructions as to how to use it, if that sold well, then we would focus our attention on how to develop an integrated variant of that. So the Nadia product, which was what I mentioned was my favorite, was actually something which went through that whole life cycle in about 2 years. So a paper was published, or 2 papers were published in Cell in May 2015, talking about using microfluidic droplets to do single cell genomics. Within a week, more than 100 people had come to our website and said, we want to do what this researcher in Boston is doing. We thought that was interesting. So therefore, we put a Lego set together within a couple of months where we validated it worked to the level required. And then had up to 700 people, 700 different teams bought our systems in some way or other over the following year and a half. But in parallel, we realized that the Lego-like stuff now, it was pretty clear what the systems needed to do. And the Lego-like stuff was a bit too tricky to use for this very fast-growing user base because they weren't specialist microfluidic engineers, they were biologists. So we then put the specification together for what became the Nadia platform and then developed that over the following years. But we had the ability to sell the components, the Lego set, to learn about what the needs of the market were before we put the spec together for what became the Nadia platform, if that makes any sense.
Yeah, I don't know so much about engineering, but the Lego set sounds like a proof of concept to me. And I do have a follow-up question for you, Mark, and then I also have a follow-up question for you, John, a little bit later. When you develop the complete product based on the feedback of the customer on that Lego set, at what stage would you involve the customers in the development? Because you know that this is...
We know, exactly. So we didn't involve the customers in the development of the Nadia platform until it was pretty much done. I mean, as in the engineering decisions had been made and it was there and it was ready to go, because we had so much feedback from the marketplace about what was going on with the existing systems we were selling, the Lego-like systems. We didn't need to show them the product to be able to prove to ourselves that it was interesting. So if you go from nothing to having a first integrated minimum viable product, then you might do a bit more market testing and discussion along the way. But because we had it in parallel, the users were just using our modular systems, our Lego-like systems all the time while we were developing that. So we kept getting more feedback, but we were pretty convinced that was right. The one comment I'd have about talking to customers is that you have to be very careful with the questions you ask and the way you interpret the answers as well. So if you've got a phone and everybody's got a phone and you say, would you like to have longer battery life and a nicer camera? Everybody would say yes. And therefore it's very straightforward for the companies to know that they can go about investing in better battery life and using less energy from the electronics and better cameras. But if a touchscreen phone hasn't existed before, and you say, would you like to have a phone that also does email and it's a camera and it also can watch movies on it? It seems confusing to you. It might be difficult for some of the audience to realize this, but 20 years ago, that didn't exist. And the idea that you could combine all these things in one device seemed impossible. So you'd say, well, no, that sounds confusing. There were a lot of different types of product that were released in, I guess, 2003 to 2007 or so, which were all prototype variants, different sorts of combinations of features most of which didn't get it quite right, but each one allowed different companies to learn something about it. Yeah, the iPhone was actually quite late to market, to be honest, amongst all the other things that were going on, but they could watch how well the other products were doing before they launched their first product. And then since the iPhone was launched, then pretty much all phones have been a bit like that. I mean, not dramatically different, lots of software features that are different, but all I'm really saying is that the discussion with customers, once you've got an established understanding of a need, then it's easy for the customers to understand what they'd like more, better battery life, a better camera. But if they don't even know what the product is, it's very difficult to actually talk to them about it. So you have to have a certain level of care in how you ask questions and also how you interpret the answers. That's the primary point I'm making.
I think that's the real challenge for many microfluidic startups, because the microfluidic technology, it brings in lots of innovation and new application to different areas. Yeah, so the follow-up question to you, John, you mentioned earlier about a sub-minimal viable product. Am I right if I consider it as a kind of prototype? And for the development of, it's a middle point to the final product. A prototype is like a middle point to the final product, right? How do you can you help me to explain that concept of developing from prototypes to products? And then there's maybe some helpful frameworks that you can recommend to ensure that you are in a focused track and also be able to develop rapid and high quality prototype.
I think
wow.
I'll say one thing first, then John, I'll let you do the talking. But I think the one thing it's really quite important to distinguish is the difference between a commercial decision about what the goal is, as in what is the product we need that we think there's a market for, and then how, as engineers, we go about developing that product. So I think that what I think is quite good, John, if you talk about how you would attack the process of developing a product.
Well, what I was going to say first up was just to reinforce what you were saying earlier, Mark, about how you ask the questions. And you ask different sorts of questions at different stages of a product development. And at the beginning, you need to focus not on the product, but on the opportunity. And there's kind of research methods called things like jobs to be done analysis and opportunity discovery, which really focus on discovering from users and other stakeholders what it is they're trying to achieve, what it is that's valuable, and what it is, what are the gaps, what are the things that are hard that they need to achieve that are currently difficult to achieve, what is it that's under delivering in their current set of tools. And that sort of research still involves talking with users and other stakeholders, but it really doesn't involve saying, look, how would you like a thing that has a screen and it makes phone calls and you can watch films and you can do this and that. That sort of style of research comes much later, as you said, Mark. And then I think in terms of development, the first most important thing is to get that right, to really understand what the value that you're trying to create is. How is your product valuable to your user, to your customer? And then I think in terms of the engineering, when you need to make prototypes, the key thing really is to make lots of prototypes and to figure out how to organize your development so that you can make prototypes quickly and make mistakes quickly and then fix them quickly. And if you get that iteration going fast, then you can get your product development going fast.
I think the one thing which I think is the part which I was thinking would be good to talk about, John, is the concept of product development phases and structures in product development to do with what the different phases are that you go through, because some people haven't necessarily come across these concepts before. And I think that prototype falls in the middle of there, but for a scientist, it isn't necessarily the way you would think about it. But why don't you talk about that a bit?
Okay. So I guess if you're in a science phase, you're in a research phase where you're trying to prove prove that you've got something, prove that you've got something that does something. When you move into, and we might call that proof of concept, and typically that would end up with something that sits on a bench and you might have lots of wires or tubes hanging out of it. But it does the thing that, in terms of the core science, it does the thing that you're intending your final product to do. Along with that, as I mentioned, you have to figure out why that thing that you've got is valuable to people, and so that your product development can focus on really making that value accessible to your users. And then you start to get into the engineering, where typically the engineers will take what you've done and they'll go, oh, that was nice. You need to do it a totally different way if it's going to be a product. And they'll come up with a different way of achieving the same thing, a more producty sort of a way, a more reliable, a more engineered, a cheaper, a smaller, a faster way of doing the same thing, of turning what you've got on your bench into something that could become a product. And that will be called a concept or a feasibility study. And once you've got that sort of engineering concept going, then you can start to make, and you've tested it and you've shown that it does the same thing in a more engineered way. Then you can start to think about making an alpha prototype. An alpha prototype, in my opinion, really focuses on proving that the main things that you need to do really work. So the main risks, the main challenges have been addressed, but it's got lots of features, the more peripheral features that don't work as well, and you're not going to make very many of them. And then your beta prototype, it does everything that the product has to do in the way that the product is going to do it, but you're not yet ready to make lots of them because you still have to transfer it into production. And so those, I think, are the sort of four main phases: the concept, the alpha, the beta, and then the transfer into production. Now that varies quite a lot. Like if you're going to only make 10 of your products, that looks very different. I've worked on products where you only make 10. I've worked on products where you're planning to make 100 million. And those phases scale accordingly. That transfer to production phase especially can take a long time if you're going to make hundreds of millions. Whereas if you're only making 10,
if you're going to make 10, then basically the production is going to be very close to the beta prototype in simple terms.
Exactly.
Whereas actually, if and you can use the same production methods largely as well. Whereas if you're going to make 100 million or something, then nothing you did in prototyping is relevant at all. You've got to spend loads of time, money, and effort on tooling and documentation and lots of other things. Yeah, and it could cost a lot of money as well. Whereas if you're developing,
I think the key point there is that there is quite a long path from having some science that does something to a product, especially if you're going to make that product in reasonable numbers.
Yeah, I think that is a very valid point. Is that the most common failing of startups in microfluidics is that there's an academic lab that has done something that's been published and it's good and it works well in the hands of those researchers. So therefore, the premise is that the startup can just take that and replicate it and sell it to other people, and then it doesn't work at all when anybody else is using it at all, because they haven't quite realised that that team has got a lot of institutional knowledge that makes it possible for it to work. Whereas it requires a rather large engineering effort to go from that apparently working system to a system that can work in anybody's hands without it being a big problem.
Yeah, so I see here the huge difference between something like with the right science and being able to do the job. But like Mark mentioned earlier, perhaps you also want to give that something to the customer pretty early so you can somehow validate the market. And then the other problem is on scale-up manufacturing. Is the product that you create, have you tested its ability for scale-up manufacturing and also to perform in every lab, even if it's a very large scale? So is there any problem that, my question is, you should only worry about scale-up manufacturing after you have the second prototype? Or is there something that perhaps you need to worry early on in the development? Because if it's too late, then you cannot go back and change.
I think that fundamentally, if you think about having a robust product, which is a product that works well and people like, if you work from the customer end back towards the beginning of a project, the first thing is they have to like using it. They have to like using it, which is a soft factor. It has to be easy for them to use. It has to gain a benefit to them easily without them having to spend a lot of time learning something they don't really want to spend their time learning about. So if it's possible to have a concept for a product at the beginning, it's going to make the life of the user easier, because it's going to be simple for them to do it. They can literally get it out of the box and press the button and it works, rather than having to spend weeks learning and training. That's good. And it is possible in many cases to take a product which could be a very easy to use product, but make it very complicated in various ways because of not such perfect decision making through the both specification and development process. The next layer back beyond that in terms of what makes it robust is having products actually reliable. It just works reliably. That means that, number one, the user can't make it not work very well by accident, by just not following rules well enough. Like, it has to naturally be designed in a way so that it can only be used one way, and that's the correct way. Together with, it has to be engineered in a way so it's at an engineering level reliable as well. It doesn't break down all the time. If you drove a car and it broke down all the time, then that would be irritating. And then further back into that is, before it can get out into the hands of a customer, it has to be able to be robustly manufactured as well, so that, again, the skills of the people who are manufacturing it can be at the lowest level possible, so they can basically get some parts and throw them together and it just works because they've been designed well enough and manufactured well enough. All of this stuff goes all the way back to the beginning of the concept. And I think it's fair to say, from my point of view, you get a better product at the end if you think through at the beginning conceptually how you're going to end up with a highly engineered, manufacturable product that's going to be robust in the face of the real world and easy to use for the customer at the end. A lot of that comes at the very, very beginning. So I think investing some significant effort in the concept development of that product, at not just what it looks like on the outside, but how it's going to actually work and built inside, at least conceptually, is a good idea. I don't know, John, if you disagree with me, but that's what, at least that's it.
No, you probably saw me nodding my head a lot as you're saying that, and the usability, and also the cost, and also the reliability. So many of those things depend on the big decisions you make at the beginning of the project in the concept phase. Now, I did want to introduce an idea that I've learned and is very powerful, because it can be difficult even for the best engineers to know what is the best concept. You come up, for any particular thing, there's usually a handful of ways of doing it, and it can be hard to know which is the best. And one of the things that you can do, which can really help there, is, first of all, if it's a complex product, break it down into smaller chunks. And then for each chunk, have 2 or 3 concepts, a plan A, a plan B, and a plan C, and you can proceed in parallel with those. And when it's a complicated product, you often find halfway through that your plan A turns out not to be as good as you thought. And in fact, I think nearly all engineers know that when they get to the end of a development process, they get to the end and they go, oh, if I only had known at the beginning what I knew now, I'd have done it a different way. But if you have those plan A and the plan B and the plan C up your sleeve, and you have to work on them all, then you can easily change your mind as you go through. And that sounds like you're going to spend a lot more money on it, but actually it turns out, when you run projects in that way, it usually turns out cheaper, because you always things always go wrong. You always have to revert somewhere along the line to a plan B or a plan C. And actually it turns out to be faster and cheaper if you design your development process to have that in place all along. And so that's really just a way of saying, kind of keep your options open as you do the engineering.
And I'm slightly aware that some of the other things I could comment on this topic, which are going off in a slightly different direction. But I don't know about time. I don't know if we've got time to do that. If you've got some more questions you want us to address.
I only have one more question from the audience who sent in, like some question people sent in earlier. You can go on, Mark.
Yeah, so I think that when you're conceiving of a product, the other thing is that there's a balance between what's lower cost to develop and what's better for the user. That doesn't necessarily only mean adding features. So you can talk about adding features, but also when it comes to user factors, you could develop it so it's going to be easy for the user at the end, but that might make it more difficult for the engineers developing it. So through that process, you need to have the right balance. There needs to be a tension between those two things, because if you just make everything that's going to make the user's life nice, it's probably going to be expensive. It might be unreliable. It might be expensive to develop it. Whereas if you make it so it's cheap to develop it and it's going to be robust to manufacture, it might be irritating and crappy to use it. So that balance has to exist. So therefore, through the development, there has to be somebody who's got the champion of the customer's use mode, and somebody who's got the kind of eye on making it cost effective in manufacturing. And that ideally would be people who are actually in the R&D team itself, not a commercial person who's specifying something, but actually champions of both ends of the spectrum through the middle of the process. And I think that one thing that's really valuable is to have decision-making processes when you're trying to make the big decisions that John was talking about earlier in the project, where you have some kind of rationalized methodology that you're applying to help to get the team to see eye to eye. Because sometimes if somebody's just saying this is the best way and another person says this other way is the best way, but they're not breaking that down, well, this one might be the best way if you're thinking about making a better quality product for the user, and this might be the best way if you're focusing on the cost of manufacturing or the robustness of manufacturing. But actually, if you just argue with a bunch of engineers and say, I like this idea and I like this idea, and you're not very good at breaking it down into what aspects of it are the things that are better, I think you probably wouldn't find there's very much disagreement amongst the engineers if you said, well, which one is actually going to be nicer for the customer and which one's going to be more robust to manufacture. That probably wouldn't be really an argument point, but it becomes an argument when it all gets tangled together. So therefore, having mechanisms to actually score rationally different aspects of concepts, so you can make it so that there's a compound score for value based on what we think is more important. Do we think it's more important to have a nice to use product, or do we think it's more important to have a cheap, robust manufacturing method? So it's just one particular example, but all I'm saying is I think that having rationalized scoring methods to make decisions about things is a good idea.
Thank you, Mark and John. So it's very nice to have different plans in your development ABC, and then to have a scoring system to help you on track. So I have one last question from the registrant. I think this question came from someone who perhaps has something already work in their lab, and they think that in order to get to the end product, they might need some engineering consultancy. But the question is how to decide what development they should do in-house, what they should outsource to a consultant.
Shall I go first on that one, Mark?
Yeah, you go first, John. Yeah.
So I think that the minimum you can do in-house is setting the direction. You have to take responsibility for that yourself. That's what I think. I also think another minimum thing that you have to do in-house is, even if you want to outsource all of the engineering, you have to have an engineer of your own who can judge whether the people you're employing are doing a good job and basically keep on top of them. That's the absolute bare minimum. Of course, on the other end of the scale, you could not outsource anything. Now, I guess the big disadvantage with saying you're going to hire everybody to do your job is do your development is that your product, it might not need all that much of a physicist, or it might not need all that much software in it. I don't know. And your product, if you hire your own team and you only need half a physicist for 6 months, then that's quite painful, because you're going to have to employ a whole physicist, probably permanently. Whereas if you outsource it, you can get the exact blend of people. For you find a consultancy that can provide a multidisciplinary team, and they can provide the exact blend of people that you need at each different stage, and it can save you a lot of headaches in recruitment, I think. I think the other thing, of course, that you have to be mindful of, and people are mindful of, is what core competencies you are developing for yourself and that you want to have in-house, so that you can carry on working on your product roadmap. And then the other one is intellectual property. But obviously that's more about the terms of business. And if you've got a consultancy that's not giving you the intellectual property that you need, then you need to find somebody else to work with.
Just coming back to one point John said, I think that the bare minimum isn't that you just set the direction. You actually also have to have enough money to pay for getting there as well. So,
yes,
that's the other part of the puzzle.
Yeah, you have to have the ability to raise funds.
Yeah. So whether that's the money to recruit your own team or to pay the consultants is that's just up to you, but you have to have the money. But coming back to this point about, I think, is that the one thing which is actually quite common in startups, especially in microfluidics, is that you need quite a lot of different skills and knowledge, like John's saying. And as John rightly says, you might just need a bit of a physicist, and you need a bit of this and a bit of this other thing. You tend to end up then therefore raising money and recruiting a team of people that have got all those skills. Now, if you need one physicist, but you're only using them half the time, you'll probably use the physicist for something else as well. But once you've got your first product and it's now ready to manufacture and sell, naturally what a startup does is it has those people who were the R&D people start doing some of the other jobs. They start evolving themselves to do more manufacturing, or they start evolving themselves to go and do demos or to support machines in the field, or even sales or something else. Now, that's fine to some extent or other, because some people will be developing themselves in really good directions. But having said that, though, you could recruit somebody else who's just really good at manufacturing, or somebody else who's really good at customer support, or somebody who's really good at doing applications development, or really good at sales. And when you take a team that you've recruited yourselves, it's very uncomfortable to make them redundant just because they've done a good job and developed the product. It doesn't feel very nice. So actually, if you use consultants and have a minimum internal team, it means that you can recruit the right people at the right time as the company develops. And you don't have to go through phases of redundancy. So you end up, you have a company that's been doing R&D for 2 or 3 years. That team naturally will end up staying there, being leaden boots financially for the company. What I mean by that is it'll be expensive to have that team sitting there when you don't really need to be as a company developing more products right now. You need to go and sell the product you've got and manufacture the product you've got. And actually, it's something, I've struggled with this a lot, but actually when a company gets bigger, it's okay, because you have sales coming in the door, you've got manufacturing going on, and you can have an R&D team working on this product, and then it can go and work on the next generation product, and there's enough money coming in from sales to fund everything, and it feels like the right thing to be doing. But it's just that the biggest challenge is that you need to have the right number of people at the right time to not burn too much money. And although consultants are more expensive in general than having your own team, if you recruit them in the same region where your team is, they will have the benefit that once you finish this project, then it's finished, and then you don't need to be spending money on them anymore. So that means you can carry on and spend the money on the right things instead for your stage of business development. I don't know if that makes any sense, Anne.
Yeah, thank you. So I think there are lots of things to consider when thinking about outsourcing, with the technical part and also the business part. That's all the questions from the registrant who sent us in advance. Thank you for those questions. And I see 3 questions in the Q&A right now. So I will unmute first Samson. He got a question on the minimal viable product. So yes, Samson, can you join us? I've just unmuted you.
Oh, no, Samson, in your garden, Samson.
Yes. I'm multitasking.
In the winter in England, it doesn't seem like the right thing to be doing, being in the garden.
It's quite warm today. Right. Okay. So, well, I have my question is back to the theme of minimal viable products. Because the thinking of minimal viable products, I mean, obviously it's very strong in sort of Silicon Valley startup culture, and it's all about the sort of mass market product idea, right? Because of course, that startup has to get to the mass market, so testing out this minimal idea. I suppose, I mean, what I wonder is for for scientific tools, microfluidic scientific tools, say, often that may not be minimal enough, because often a lot of investment is required even to get that. One moment. Often a lot of investment is required even to get that. Is it this sort of the mass market angle on that? I wondered if maybe that's a limiting factor. So for scientific tools, say microfluidic scientific tools, one could be even more minimal if one doesn't have the mass market in mind. If it's serving 1 to 5 customers, doing something useful, then possibly something even more minimal could be developed for even less money, say before the commercial opportunity is proven. That was the idea.
I think, Samson, that in the context of the science environment, our big numbers are still, by any other world scale business, teeny niche markets. Because I mean, if you're talking about a scientific market where thousands of people might want to buy something, that's actually quite a big market in science. Hundreds is more common. If it's in medical devices, in medical stuff, it's slightly different, because that could actually now be many people. But in the scientific world, it's very usually at most thousands per annum, but more commonly hundreds. And actually quite a lot of businesses do quite well out of 50 to 100 units a year of whatever they're selling as well. So I think that by nature of that, we are talking small numbers anyway, not really mass market. But having said that, though, I think the balance of, if you're going to aim to develop a product only one person might want to buy, that doesn't seem like a very good idea unless it's an incredibly low development cost to develop it.
Well, I mean, just to take the thought a bit further. I mean, obviously, one of your examples would say the iPhone. Obviously, that's a very bold decision. Involved a lot of features in a single thing, right? And of course, it was successful. But then there are a lot of things like that which are not successful. And I mean, say talking about scientific products. I mean, also microfluidics. I can think of, I mean, having been in a company that both of you have been in as well. I've seen a lot of things that say where the supposed minimal viable product was not actually correct. It was not actually the right product, but they thought it was, and say they've spent say millions, tens of millions to get there. Perhaps that's just not minimal enough. I mean, if it takes tens of millions to get to a minimal viable product, and then the minimal viable product fails, that's not minimal enough.
Well, I think the fundamental point, Samson, is you're right. If you really don't know the market, you should spend tens of thousands of dollars on developing something really minimal that you can test the market with for real, like you can sell. The reason I'm saying this is because if you go and ask somebody, do you like this? Would you buy it if it existed? There's not much skin in the game there. But if you actually say, you can buy this now, do you want to spend your money on it? If it's not £100,000 or $100,000, if it's $1,000 for them to have a go at something little, and it proves something, that's a really interesting market testing mechanism to have a really minimum product. So I do agree with that. And that's what Dolomite used to do with our web shop of standard components. We would have, for example, a few people might ask for the same sort of thing. And then we think, well, there may be some chance to make a standard thing. So we develop a custom chip or a connector or something that might cost us, I don't know, $10,000, $20,000, $30,000, $40,000 to develop it. And then we launch it and see if anybody bought it. And if people bought lots of them, that was interesting. If they didn't, then we didn't think it was interesting. Sorry, John, were you going to say something?
I was just going to say, in the story that you're telling, Samson, thank you for the story and thank you for the question, by the way. I think you're right. But I think that in that scenario, you don't necessarily have to sell a product as such in order to test the market. You can sell, alternately, you can sell a service. So if you've made one of your thing, it might be you can prove the value of what it does by selling people an experiment on your thing or some time on your thing, and they don't have to spend £1 million on this massive thing that you've only made one of. They get the value out of it. You understand better the value that they're getting from it by selling a service instead of the product. What you think of that?
Oh yeah, thanks. Yeah. No, I do appreciate those thoughts. Yes. Yeah. Yeah.
Okay. Anne, are there some more questions you say or comments?
We have another question from Elliot, but I don't see him here.
Oh, is Elliot not in the meeting anymore?
Yes, maybe he got disconnected. So I'll just read the question for you. He said that he got some recent discussion with the investor and stakeholder thinks that there seems to be three main hurdles to microfluidics. One is the production rate. Can you produce it at mass scale? And second is connectivity, how to connect the chip to the sample. And third is sample preparation. It seems like sample prep is often overlooked in platform and system development, and it's a key point. So maybe if you have any sharing about those 3 points.
Well, I think it's fair that it is necessary to be able to have the visibility of how you're going to make the thing that you've got a concept for at a production volume that's suitable for the market opportunity you're going for. If you can't see that it's possible to do it at all, then why would you bother developing it? Because even if you get to the point you've got a successful prototype, you can't make it. So I think that Elliot has some very high resolution 3D printing technology. So you could find that some of that is quite relevant to his customers because they basically will be getting him to make things that are really, really difficult to make by any method at all other than his methodology. And therefore he has to prove that he can actually make enough of them for their application, which I think he probably can do in some cases, yes. But it depends on whether you're talking about something that needs to be made in 100 per year, 1,000 per year, 10,000 per year, 100,000 or a million or millions per year. And in microfluidics, you tend to find if it's something in a life science tool environment, if it's not in biology, then it'll use hard materials, glass or silicons or whatever, and those parts will be used again and again, and they might only be made hundreds of times a year for the machine, because once they're in the machine, they stay there and just get washed and used again and again for maybe even years. And then there's the other end of the spectrum where even in the same sort of marketplace, life science tools still, you need to use a device every day. So each machine in the install base will have to use 200 devices a year because they're going to use one every day, every working day. So 200 devices a year. And if the install base becomes 1,000, that's 200,000 devices a year. So therefore, the numbers can very quickly get into the hundreds of thousands. So you've got some devices at the hundreds and some at the hundreds of thousands. And I think that the question really becomes focused on, can you actually make this stuff in the large volume disposable world of plastics? And then it's more down to, if the development work has been done with one fabrication technique and that isn't, you can't use in high volume manufacturing, like PDMS molding, for example, then yeah, I mean, this is a relevant question. This is a relevant question. I think that's the first part. Connectivity, yes, connectors, how you're going to get things in and out of the chip is always important. And I think that the bit to do with sample preparation, yes, if you've got a bit of meat and you, as in a physical bit of human tissue, and you've somehow got to do something with the DNA of it, you've got to somehow disassociate that tissue and do other things to it in advance. And I think that many times the startup minimum viable product will expect the user to do all of that manually themselves before they present the sample to the machine, to the microfluidic system, and that can make the product very unreliable and variable in its behavior, because that sample preparation is done by somebody themselves without really necessarily having known what they were supposed to be doing exactly. So I mean, I do think these are definitely hurdles. I'm not quite sure whether I'd say they are the hurdles. They are very significant hurdles, but I wouldn't necessarily say in every application they are the hurdles. I don't know, John, whether you've got a different view on it.
No, I think you've summarised it nicely there, Mark.
Yes, so that's all the questions we have in the Q&A chat box, unless the audience today if you want to send in more questions. I just want to come back to your last comment, Mark, on connectivity and then sample preparation. Do you think when developing the product, like the engineers or with your experience, do you see engineering solutions to address those problems?
Yes. I think that the common challenge, I think, which I see again and again, is when you have teams that raise finance because they've got some clever intellectual property, they frequently underestimate the actual disciplined engineering work that's required to turn it into a robust product that's going to be useful to the customer, really. And I think that if you look at lots of the universities that have spin-outs, they will emphasize the intellectual property and the scientific discovery, which is really, really, really critical part of the puzzle. Because if you don't have the science bit working, the new science bit that's going to make the product justify itself, then it is critical. But all the things that are mentioned there by Elliot are really just hardcore engineering things or manufacturing things, either product development things or manufacturing. So the chips question is about manufacturing and understanding the fabrication methods that exist in the world and how to design a device so you could exploit what exists as high volume manufacturing methods and still meet the needs of the kind of functional technical things you need to do. And the rest of it is also just to do with disciplined engineering process of developing a product, which is not the same as the scientific discovery components at the beginning. I don't know that quite that's quite what you were asking, Anne.
Yes, thank you for the answer. A little bit more on the discipline in developing a product. So I was wondering, is there any quality management process that you would apply to the development similar to like manufacturing?
I want to chip on that one. So I think there's a couple of things that require a lot of discipline. So the first is that when you get to launch a product, and the quality management side of things it can be critical depending on the regulations in the industry. You know, you could go to jail if you don't comply with everything you're supposed to comply with. But even when that's not true, if you're manufacturing something, in order to make it the same every time, you have to have, and therefore to make it consistent and reliable, you have to have processes in place, and you have to make sure that the people who are doing it comply with the process, and that the process only gets changed when you know it needs to get changed and the changes are properly proven before they're rolled out. So that's a QMS process, and you definitely need that when you're making stuff. When you're developing something, I think that you have to be really careful to be disciplined about estimating how far you are in the process. It's very, very easy to think that you'll have nearly finished developing the product when actually you've still got lots and lots of problems to solve and a long way to go. And the reason why that's important is because when you have nearly finished the process is you start adding all this QMS stuff, like design controls and change controls that stop you from changing anything without good reason and without good proof. And the problem is, if you do that too soon, then you're doing that in a phase when you need to make lots of rapid changes. During the development, the key is to make changes fast. Once you finish developing, you're making, the key is to make changes slow. And if you switch from fast to slow too early, then your development process really gets bogged down in that QMS stuff. And so you have to be very careful about thinking you're further on than you are. And the key to doing that is to design your development process with milestones. So you say, well, once we've got this, once we've achieved this very clear objective, then we can say that we've done our alpha. or once we've achieved this very clear set of objectives, then we will say that we've done our beta prototypes and we're ready to go into the next phase. And to try, it's always tempting to fudge those, but it can cost you dearly if you try and progress, if you go through those stage gates before you're ready.
Mark,
Can't hear you, Mark.
Sorry, I'd muted my microphone. Part of it's connected to project management as well. Is that you have to have described, defined goals, which are a combination of time, cost, and the goal itself. You know, I'm going to do this for this much money in this much time, and this is a defined thing. There are different types of project management methods by which you can go about doing these things, and they have different value in different scenarios. But at the end of the day, it's important to write things down and say, this is what I'm going to do by when. And the reason why is because if you just work together in a good way in your own mind, you can get this creep of what the goals are and a creep of what the money was you were going to spend, and everything creeps and you actually don't really know. You don't even remember what you said you were going to do and when you're going to do it. But by writing it down, even if it's just a one pager that says we're going to do this stuff in this much time and this is how much money we're going to spend to do it, that helps, because it means you've got a baseline to say, well, this is what we need to be doing, and it stops you just drifting onwards forever. The other point which John was making was to do with the idea that you need these stage gates, get milestones, gates that sort of prove things along the way, and that is connected to the project management. It is sort of extra as well, is that you need to have a very clear way of documenting precisely what the goal is, which is the milestone that you're talking about, John. And those things in combination can really make something that's really effective. I mean, it really can make something effective. But again, it's a balance between discipline and structure, which is necessary to some extent, but too much of it, as in manufacturing, got lots and lots of discipline and structure, and you can't change stuff. And you don't want to change stuff, because in manufacturing, you want to make something reliable. And in R&D, in the early stages, you want to be able to have a lot of freedom, because you want to be able to change things a lot. So it's how much discipline and structure to apply to still enable you to innovate. And it's this sliding scale of discipline and structure versus creative freedom. And there is a need to have a change of mentality at some point. But I think there is a certain level to which, actually, John, it's gradually evolving through those different stages. When you've got a concept phase at the beginning, you've got a blank sheet of paper. When you've got an alpha phase, you've got some freedom. A beta phase is already closing down. Production transfer is closing down further. And when you're actually in production, you're closed. You can't change anything anymore now. So, or at least not without a complex process or a disciplined process. It's an involved subject space to make the right decisions about how much discipline to apply.
Yeah, thank you, Mark. It's a good reminder that you need to keep the room for the engineer to create, but also have discipline for them. There's a comment on this topic from Matthew. So Matt, I will unmute you. If you want to share something about this, please speak up.
Do you want to read out his comment?
I can see him there, but I just cannot hear him.
I can explain what he said. I think I understand what he means. TRLs are technology and readiness levels, and there's a defined set of ways of describing different TRLs. I think it might have come from the American DoD or something originally. I'm not quite sure where they came from.
It originates in the aerospace industry.
Yeah, aerospace, yeah. So, but I can't remember how many levels there are, but each level is to do with how close it is to being a product and how far away it is from being a product, and how ready the technology is as something that go there. And simplistically, yeah, is how strictly you apply the quality manual to what you're doing, depending on the technology readiness. So that is valid to some extent or other, I think. Yeah.
I think that's right. I think that TRLs is a useful concept, but they do refer to technology readiness levels. And I think there's a difference between a technology and a product. I think that you have to sort of take that concept and translate it into a kind of, if you like, product readiness level. Because when you look at the TRLs, they aren't brilliantly adapted for a product development.
Yeah, thank you for the comment. And it's unfortunate that Matt said the computer security stopped him from using the microphone. But
That's frustrating.
yeah, thank you so
He
much.
said it's NASA. He said it's NASA, not aerospace. But anyway, I mean that's aerospace, but space.
Yeah, NASA is part of the aerospace industry.
Yeah.
Yes. So I think that's all our questions for today. It was a very helpful discussion. I learned a lot, and I hope the audience also learned one thing or two. And yeah, thank you, Mark and John, for all your sharing today. We now have so we have a survey at the end for the audience to rate this episode, but also we have a quick poll now. If you want to join our next episodes, the next episode will actually be on a fabrication method. You can let us know in the poll, and then we'll send you the invitation to the next episode. Yes, and please vote so that we know if you want to attend the next one. And also, please help us to fill in the survey at the end so we know is there anything that we can improve for the next episode. And we'll send you the recording and all future updates through emails. With that, that's all my part for today. Mark and John, do you want to say anything to say goodbye to the audience?
No, well, thank you very much for coming. I hope you found it interesting and helpful.
Thank you very much, everybody. Good to talk to the people who've responded as well, who've asked questions. Thanks very much for the questions.
Yes.
Bye-bye.
Bye, guys.